Welcome to this webinar. My name is Christopher Seidel and I'm responsible for the technical marketing of MDK and CMSIS. In this webinar, you'll learn how to unleash the DSP capabilities of ARM Cortex-M based microcontrollers. Using ASN's Filter Designer tool, you can generate CMSIS-DSP compliant code that can be directly imported into Microvision. Enhanced features such as the logic analyzer display the waveforms of your input and output signals. I'm here with Dr. Sanjeev Sarpal from ASN in the Netherlands, who will tell you more about the Filter Designer, its capabilities, and give you a live demo how to create CMSIS-DSP code, export it to Microvision, and use it in our tool. Now, why do we need digital signal processing? The smart systems around us generate lots of data. They come in all varieties: audio, humidity, temperature, or weight sensors, for example. They all produce measurement data that needs to be processed. This data includes unwanted components like white noise, power line interference, or glitches. These unwanted components need to be removed using filters. And that's where digital signal processing comes into play. The DSP, or digital signal processor, has been around for years, providing engineers with a numerical powerhouse for demanding signal processing applications. Strengths include unmatched arithmetic performance, very high clock rates, and a good selection of devices to choose from. However, the weaknesses of the DSP are significant. They can be very difficult to program, frequently poorly suited for high-level languages. Exactly this high-level language support, and of course ease of use, was the main reason for ARM to come up with CMSIS. CMSIS is ARM's Cortex microcontroller software interface standard, which is a consistent software stack or abstraction layer for all Cortex-M processor-based devices. There are a lot of benefits to the embedded developer using CMSIS. The consistent software interfaces help you to reuse your code on multiple applications, projects, or cores. It reduces the software development cost and shortens the time to market. The CMSIS-DSP software library is a suite of common signal processing functions for use on ARM Cortex-M processor-based devices. It is divided into a number of functions, each covering a specific category. It has separate functions for operating from 8-bit integers up to 32-bit floating point values. It specifically utilizes the capabilities of the ARM Cortex-M processors and scales from Cortex-M0 up to Cortex-M4 and M7. The latter ones provide additional SIMD capabilities which make them an excellent target for digital signal processing. In this webinar, we will use filtering functions, which are one aspect of the CMSIS-DSP library. It supports IAR, FIR, and LMS filtering functions, each supporting a different use case. KyleMDK is the most comprehensive software development solution for ARM-based microcontrollers and includes all components that you need to create, build, and debug embedded applications. The MDK tools contain the Microvision IDE, debugger, and ARM compiler with leading support for ARM Cortex-M devices. Software packs add device support and software components that you can use as building blocks for your application. They may be added anytime, making new device support and middleware updates independent from the toolchain. MDK middleware provides royalty-free, tightly coupled software components that are specifically designed for communication peripherals in microcontrollers. MDK middleware is provided as part of MDK Professional or MDK Plus in binary format. CMSIS itself is provided as a software pack. In our example, we will use CMSIS-DSP and KyleRTX, which is based on the CMSIS-RTOS API. And with that, I hand over to Dr. Sanjeev Sarpal, who will tell you more about filtering and designing filters with the ASN Filter Designer.
Thanks, Christopher. Welcome to this webinar on digital filter design with the ASN Filter Designer and generating CMSIS-DSP compliant code for Microvision. My name is Dr. Sanjeev Sarpal, Director of Algorithms and Analytics at Advanced Solutions Nederland. The presentation today will start with an overview of sensors and then lead on to the advantages and disadvantages of analog and digital signal processing, followed by a live demo where we would design, test and deploy an IAR filter to Microvision and verify the results in Microvision's logic analyzer. So, let's get started. Sensors come in all types of shapes and forms. There are sensors for audio, pressure, temperature, weight, strain. The list is almost endless. In all cases, sensors produce measurement data, which are comprised of unwanted and wanted components. Examples of unwanted components include measurement noise, power line interference, and glitches. So the challenge for every designer is first to identify what aspects of the data we want to keep, that is, the wanted components, and what we need to filter out, the so-called unwanted components. Let's have a look at a classic sensor measurement problem using a load cell. For those of you unfamiliar with this type of technology, a load cell is a strain measurement sensor that is comprised of 4 strain gauges. It's also referred to as a Wheatstone bridge, hence the terminology bridge sensor. Looking at the hardware setup, we see that we have a load cell excited by a DC excitation voltage. And the general idea is that the sensor's differential bridge voltage is amplified by the instrumentation amplifier when strain is applied. The differential voltage is passed through 2 filters in order to remove power line interference and reduce measurement noise. So let's have a look at some pros and cons. The instrumentation amplifier has high impedance inputs, which makes it easy to connect EMI filters to the inputs. However, any mismatches with these filters would generally degrade the instrumentation amplifier's common mode rejection ratio, which is undesirable. The instrumentation amplifier usually has a large gain, 100 is quite typical, so any unwanted differential voltage on the inputs will be amplified. Looking at the filters, the notch depth of the 50 Hz filter will be dependent on the component tolerances and will vary over time and with temperature. We'll come back to this later. Finally, any analog filter or filters will require careful PCB layout and eat up precious board space. So let's see if digital's any better. Replacing the instrumentation amplifier with a 24-bit Sigma Delta ADC, we simplify the circuitry. Although many ADCs don't tolerate high impedance of their inputs, which can be problematic for good RFI filter design. Nevertheless, some Sigma Delta devices do have an inbuilt 50-60 Hz notch filter, which simplifies the filtering requirements, although these are more expensive and the choice of sampling frequency is limited. But they may indeed be good enough for some applications. Let's have a look at the signals that we're talking about. Breaking down the sensor measurement data, we see that for our load cell application we have 2 unwanted components, namely the 50 Hz power line interference and the measurement noise. The one wanted component we have is the DC components, and looking at the plot at the bottom we see that we have the net signal. So the question is how best to proceed. Let's look at an analog solution. The most obvious advantage is that analog filters have excellent resolution, as there are no number of bits to consider. Analog filters have good EMC properties, as there is no clock generating noise. There are no effects of aliasing, which is certainly true for simpler op-amps, which don't have any fancy chopping or auto-calibration circuitry built into them. Analog designs can be cheap, but there are several significant disadvantages that affect filter performance, such as component aging, temperature drift, and component tolerance. As with so many things in this world, good performance requires good analog design skills and good PCB layouts. And as a closing remark, one big minus point is that the frequency response remains fixed. That's the case of a Butterworth filter will always be a Butterworth filter. Any changes to the frequency response would require physically changing components on the PCB, which isn't really ideal. Let's look at a digital solution. The first impression is that a digital solution is more complicated, as seen here with the 5 building blocks. However, digital filters have high repeatability characteristics, and as an example, let's just say you wanted to manufacture 1,000 measurement modules after optimizing your filter design. With a digital solution, you can be sure that the performance of your filter will be identical in all modules. This is certainly not the case with analog, as component tolerance, component aging, and temperature drift mean that the module's filter will have its own characteristic. Digital filters are adaptive and flexible. We can design and implement a filter with any frequency response that we want, deploy it, and then update the coefficients without changing anything on the PCB. This is certainly a big plus over analog. It's also easy to design filters with linear phase and at very low sampling frequencies, two things that are quite tricky with analog. There are, of course, some disadvantages. The effects of aliasing, and if designing in fixed point, finite word length issues must be taken into account, including the limitation of the ADC and the DAC. As there's a clock source, and perhaps high-speed data lines, digital designs will produce more EMI than their analog counterparts. That being said, let's now look at the most commonly implemented type of digital filter, the moving average. The moving average filter is a simple and yet effective filter for noise reduction, where it's actually the most optimum filter for reducing noise while retaining a sharp step response. Less known is the fact that the moving average filter is a great smoothing filter but a terrible low-pass filter. As seen in the frequency response on the right, its stop band attenuation is poor and the roll-off is slow. Nevertheless, the implementation is very simple, as it's just based on addition, which is in contrast with the standard FAR filtering concept that requires both multiplication and addition. One important decision that designers have to make is what type of arithmetic do I use, floating point or fixed point? Looking back over the last 20 years or so, the floating point DSP market was dominated by a few industry titans. These devices were not targeted for low-cost sensor applications and were generally intended for expensive high-performance audio and military applications. Nevertheless, the good library support and ease of implementation from MATLAB or C was certainly attractive to many. Fixed point, on the other hand, was and still is intended for low power and low cost portable applications. However, the design time needed was significantly higher due to the limitation of fixed point arithmetic on the algorithmic performance. If we fast forward to the present day, vendors basing their microcontroller on ARM's Cortex-M4 and M7 cores offer designers the ability to implement their algorithms with hardware floating point support. These so-called enhanced microcontrollers are rapidly becoming popular in many IoT applications due to their low power and cost. ARM provides the CMSIS-DSP development library free of charge, allowing for the implementation of fixed point and single precision floating point filters, as we'll now see in the following live demo. ASN Filter Designer allows engineers to interactively design their filter by using graphical design markers. This is significantly different from many other tools that are based upon entering specifications into a text box. As seen here, we can alter the magnitude specification by dragging the design marker specification. The tool also supports many other classic design methods such as Butterworth, Chebyshev, and Elliptic. The tool's real-time design paradigm allows for real-time feedback of the design coefficients and frequency response. As seen on the left-hand side, the filter coefficients and summary are updated in real time. Okay, let's now return to our application. The requirement is to attenuate our power line harmonic frequency, so in this particular case 50 Hz, 100 Hz and 150 Hz. In order to accomplish this, we need 3 nulls. Now let's just see if we can actually reduce the filter order somewhat, such that it's a much more efficient implementation. So if we drag the designer, we still We see that we have an order of 6, 5, okay. So let's just see how far we get with 6. So we want about 40 dBs of attenuation. Okay, so what we now need to do is nudge our zeros a little bit left. Now we can do this with the pole 0 editor there, or we can use the pole 0 chart and interactively move the zeros. So if I click on that, you can see that we can lock the zeros in this case to the unit circle, and then the orange line signifies that there's a lock, and we can just use the mouse to position our zeros. So as we're interested in 50 Hertz exactly, let's just use the text box and lock that. We do the same here, so we want 100 Hertz in this particular case. And with the last one, we want 150. And there you go. We have our zeros exactly at our harmonic frequency. But now, unfortunately, we're faced with another problem. You see now at DC, which is our requirement, we're not at 0 dB anymore. So we can zoom into that region just by using the mouse wheel. Let's just rescale it a bit. There you go. Now, traditionally this would be a problem. Now, what we can do in the tool now is use this thing called locked filter gain, which specifies the gain at a certain frequency. So we would like a gain of 0 dB at DC. So it's as easy as that. Clicking on the padlock will automatically scale the filter to the desired gain. As seen on the left, the lock filter gain appears there. So within a couple of minutes, we've basically designed our filter to our specifications and we're ready to go. Now, in order to deploy to the CMSIS library, we require that we re-optimize the design, as it's a mixture of different gains, and we have optimized the filter cascade manually. We need to re-optimize the design. That's easy enough using the re-optimize menu. If we click on biquad, the tool will automatically redesign based upon the specifications we've given. So seen there, you see that we now get exactly what we want. You'll probably notice here that this is slightly different to what it was, but that's because of the zooming aspects here. So these are directly at 50, 100 and 150. Now, in order to deploy to CMSIS, you'll see that we can just do this, but then it complains that the design is in double precision, which the library doesn't support. Now, if we change it to single precision or fixed point, we can simply deploy the code. So let's just use single precision. We know from the ARM documentation that the direct form 2 transpose filter structure is the right structure to use here. So clicking on that, we see that we get our code directly for Microvision. Just to prove, zooming back out again, we see that we get the net frequency response now. So you can see that we do indeed have our nulls at 50, 100 and 150. What we can now do is test the design within the inbuilt signal generator and signal analyzer. So we can quickly set up a sine wave and some white noise and just run it. So you can see that the blue signal is the input signal and the red signal is the filtered signal. Now for this particular application we're interested in a DC offset. So if we specify that as 0.21, then we can see that we get the desired result here. Just to prove that indeed it does work, we can turn off the white noise and we can use the markers, and as seen on the bottom right there, we see that the amplitude is indeed 0.21 and all 50 Hz in this particular case components have been attenuated. Now that we've designed our filter, now we can integrate it into our microvision projects. So setting up a default project, what we need to do in this particular case is just take the relevant bit of code and just copy and paste the code directly into our project. What we've done here is just set up a test signal with an amplitude of 0.21, a 50 Hz sine wave and some white noise. And then we're just running it through the filter that we've just designed. Incidentally, this project will be available at the end of this webinar, so please feel free to play with it. Right, what we now need to do then is just save, build, and just start our debugging session. So we've already set up the logic analyzer for the input and output signals, and let's just see what it does. Okay, if we scroll back to the beginning, there you go. Let's just get the amplitude right. We see that we do indeed get the right amplitude at 0.21. And there you have it, a complete all-in-one low-pass and notch filter, completely designed, verified and tested within minutes. Well, that now concludes my presentation. Thank you very much for your time and your attendance, and I'll hand you back now to Christopher.
Thanks, Sanjeev, for this impressive demo. Now let's summarize what we've learned today in this webinar. Our development suite KyleMDK is full-featured with support for RTOS, middleware, and the CMSIS-DSP library. CMSIS itself helps you to write reusable code on any ARM Cortex-M processor. Expert tools like the ASN filter designer help you to create powerful DSP algorithms and to export them to the CMSIS-DSP library so that you can quickly use them in your microcontroller project. If you want to learn more, please check out these web pages. Thanks for listening. This is the end of our webinar. Sanjeev and myself will now take a look at your questions.